So this week we're going to continue to look at DLC3's data path and how instructions execute. It's really just some detailed examples. In reality, what you have to do is just to put things together to see how it works. It's not a difficult thing to understand, it's just a bit more complex. We are going to see some examples of that. So we're going to just go right into that example. We've been looking at these instructions. Given a particular code, 16-bit, we will know exactly what it is. And this is the exercise that we did in class. And here's the first one. And if you haven't tried this exercise, pause the video and see for yourself what it is and how it's being executed. So 1001, that's the opcode. And from that, we should know that it's an ALU instruction. And in this particular case, the NOT instruction. And what follows is you look at the next 3 bits, that gives you the destination register, and another 3-bit that gives you the source register. In the case of NOT, a single source register is needed. We're simply flipping the bit of one register. So that results in a rather simple execution data path. One source register is going to be used, and the data is going to be sent to ALU. Result will be stored back, and it's simply a bitwise flip. So perhaps the simplest instruction you can see. Next one, 0001. And if you have the instruction table with you, you would see it's the first instruction that we listed as an add instruction. And again, you look at the source, destination register, in this case, the next instruction afterwards, a bit after the source register shows that the value should be treated as an immediate. So that 5 bits, is treated as a value, not a register ID. And this is sort of the part of the data path that mattered. The last 5 bits is in fact always sent through a sign extender to be ready for computation, again in LC3. But we use the 5th bit to decide whether to use it at all. So that's the control to your mux multiplexer. You can use a source register, or you can use the extended offset or immediate value. And then you add the result, of course, you pump it back. And so suppose R4 start with a value of 110, which means positive 6. You have 11110, which is really negative 2. 6 plus negative 2, the result is 4, and that's what you get. The 2's complement representation of that value for this instruction. Next, 0010. So if you look at the table again, okay, that's 0010. That's sort of in the middle of the table. It's a load. This case, it's a load with a register R2 as the destination and the long 9-bit offset. Okay, so that's a PC offset. Again, the data path that's used in this case is highlighted in the picture down below. This is an offset x1AF, so it's a negative value. It's always 2's complement. That would be sign extended to a 16-bit value. If I'm allowed to go back to the past, this is of course all just sort of yanked out of your real data path. But if we look at this one, what we're showing here is really the adder over here with a PC coming in with a 9-bit offset that's straight out of the instruction register. Okay, so that's how we calculate the address. And for clarity, in this picture, we're only showing them in here. Everything else has been removed. So you take the PC, you add the sign extended offset, you get the result. That's going to be pumped to memory address register. Step 1, 2, you read the memory. Data comes to MDR. 3, you send it back to your destination register. That's how it works. Okay, so that's a load instruction. 0010. Next, you should try this too. 1010. It's another load. We give it a name in the table, I believe LDR. Sorry, LDI. L1010. Okay, what does that mean? Load indirect. Everything else is the same, in fact. Destination register and an offset of 9-bit. So that 9-bit will be sign extended, added to the PC. Okay, through the other over here. I get the data. The only thing is the I part. So this is your load, LD, and this is your LDI. And I is the keyword, the indirect. Okay, it's not a necessary addressing mode, but it's the one that is being supported by LC3. As you can see here, I get the address. What is I? The data that you load from memory is itself an address. You use that to do an indirect access. You go access whatever the value used as an address points to. So you get the address. The address is this. The address is this. That's adding the offset to PC. Okay, you get the address. You put it in memory address register. Step 2, you access the memory. Normally, or in the case of the left-hand side example, we get the data. In step 3, we would have pumped it to the destination register. But no, we don't do that. In step 3, we put the value back, whatever we loaded from memory, back into the memory address register. Y indirection. Okay, so that address is going to be used to access the memory again in step 4. This time we get the data, and in step 5, that data is sent to the destination. So you access memory twice. You could have done this here, for instance. You use a single load, you get the data in, and you use another load instruction to access the data a second time. But with LDI, you can do this with one instruction. It's not a great deal of improvement, but it is one instruction, one type of addressing mode that's commonly supported. Okay, here's another instruction, 0110. Another load. This time LDR. LDR. Okay, so I think there's some typo in this. By the way, these are all in the textbook. I just grabbed the picture from there, so you can read all the examples there yourself. In LDR, you have a source register. Now you have 2 registers. One that's the destination. Number 2 is the source register, and you have a much smaller offset. That's only 6 bits in this case. Again, part of the data path shown here. If it's 6 bits, sign extended, but you're not adding PC because this is LDR register based access. So you take source register, in this case are I think that's the typo, either in here or in the textbook image. It really should be, the source register should be 011, which is R3. You take the value out, you add to the to the offset, you put the result in MAR, memory address register, go through the three-step process, you get the data in. Okay, so the difference is register-based, register plus offset, or PC. Okay, so LD is PC plus offset. LDR is register content plus offset. Addressing mode. Next instruction, 1110. That's towards the bottom of the table, 1110. It says LEA, which stands for low defective address, but this is an interesting instruction in that it doesn't really access memory. See, there is no memory data path down here. What it does is very similar to load. Takes PC plus a 9-bit offset, again always sign extended, added the result, and the result is in computer jargon is called the effective address. So this is not the address, this is not the address. This is the base, that's the offset. You add them up, that's really what the address is, and it's called the effective address, the actual address if you wish. What this does is, rather than loading from the effective address, we're loading the address into the register. And that's what it does, right? You put the address rather than the data into R5, into the destination register, in this case 101. What for? In preparation for future accesses. Now you're setting up R5, perhaps to be used next time in an instruction that involves LDR, and R5 could be your base register from now on. So load effective address is sort of initializing register. Okay, it's not a load in the strictest sense, which carries data from memory to your register. Finally, let's have something different. This time, the opcode is all 0. Okay, that's a branch. And for branch instruction, it's a little different. Okay, there's no destination register. Why? Because branch instruction changes PC. It's implied. I don't need a field to say change the register into this, or change the PC into this. So what's done here is that there are 3 bits to allow us to specify the condition flag. So in the machine, there are 3 registers, or 3 bits. Later on, we will see this being called the processor status register. Maybe just to be, it's a 16-bit register, but maybe some middle 3 bits are dedicated for these. You can imagine having this status register being quite useful in the future to show what happens in the computer. It's some error is occurring, or the machine is in certain state, it's functioning. So you can imagine this word telling you information about the state of the machine. But in particular, I have 3 bits that indicated whether the result that I just created, the last operation that produced the value, branch didn't produce a value, so anything else that produced the value, be it a load or an add instruction, the value has a sign. It's either 0, Z, positive, P, or negative. Okay, so if it's 0, the Z bit will be set, the other 2 bit would be reset. So the branch is based on the condition, the conditional flag that we have now. And here what we're saying is which bit do I care about? The 3 bits in the instruction specifies that. Do I care about the N flag, the Z flag, or the P flag? And so you can see that this is a mask. It's used to go through some AND. Okay, ending a 0 will eliminate it. Okay, So if I set 0 and 0, that means I only care about the Z flag. If it's set, I branch. If it's not, I don't. You could imagine having more than one bit set. In particular, you could have all 3 bits set. And what that means is any flag, if it's set, I'm branching. And that's actually interesting because you know that the result of a computation is either N, Z, or P. One of them has to be set. So if I have a 3-bit mask in my instruction, that's really saying it's an unconditional branch. I don't care about the condition. But this is how things are wired. I take the 3 flags, the 3-bit of mask, I AND them with the 3-bit and go through an OR gate. And if this thing says yes, I'm branching. So that bit is here to control which value gets into the PC. The PC used to have a PC plus 1 that we didn't show set into PC. Now it could be updated by this new value, and that's controlled by the result of the masking. And if it's branching, we're going to change PC. If not, we don't. So the PC is already incremented, and we just execute the next instruction, and that's the end of the story. So really, we gave you some examples of how this works, right? You can play any of these instructions. Look at any one of these instructions. What happens? Some of these part, the register, ALU, or memory, will get used. And it's all shown here in this somewhat simplified data path. Okay? And that's the design of that's the blueprint of the computer. And if you are to design it, to design a machine that works, you got to figure this out, somehow describe this in certain description language so that you can have some manufacturer print this out in a circuit board for you, or in today's world, more like you're giving it to an integrated manufacturer to fabricate a chip for you. And that's really what all there is to it. This is for all practical purposes, the actual computer. It's the design of it. So we look at the data path, and you can play with all kinds of instruction. This is really how LC3 works from a instruction by instruction point of view. And next week, our job is to look at coding this with more than one instruction and how that goes.